Good evening, students. So in the previous videos I have already discussed about the Ampere's acquittal law and already discussed about the how we can apply the Ampere's acquittal law in the straight line, in the straight conductor, and as well as the circulator conductor. Okay, now I am going to discuss about the solenoid and toroid. Okay, so what is solenoid? Solenoid is a particular arrangement when there is a particular iron rod which is wound up with the conducting wire, and if we pass the electricity through that conducting wire, then what will happen? That iron core becomes or acts as the magnet, right? So this is the basic characteristics of the solenoid, and all the magnetic field through that solenoid passes through the center of that core. And now our concern is that to find the magnetic field which is produced due to the application of the current through that conducting wire. Okay, so let us start. So if we consider a particular solenoid, this is the particular arrangement of a particular solenoid. So if current flows, so there will be a magnetic field for which basically the iron core acts as the magnet, right? So in general, if it is considered north, it is south. So the lines of force just starts through here and it basically exit through this south pole, right? Now let us see how we can apply the Ampere's acquittal law here. So if it becomes the coil, I am just considering a particular rectangle through this coil. Let us name it as A, B, C and D. So this is positive, negative. Let us consider that the current is flowing like this. Okay, this is the direction of in this way current is flowing, and this is the direction of B. Let us consider this. Okay, so if there is the n number of turns enclosed by this rectangular path, and let us consider DL is very short path or very short small segment on that path AB, and B is the magnetic field produced due to this part in the solenoid. So according to the Ampere's acquittal law, what we can write? We can write basically closed integral of A, B, C, D, that will be B dot dl, right? So from A to B, one integration, plus from C to D, from B to C, another one, plus from C to D, and from D to A. So total magnetic field in each and every rectangle will become the total magnetic field due to this solenoid produced in that iron core. Okay, now have a look that in this field along this AB, whatever the direction of the B, that is the same direction of DL. That's why as this thing is same, so what will be this value? This value becomes BL. If L becomes the length of this AB. Now, this BC, whatever the direction of this B, and DL will be in the perpendicular direction. So, cos 90 becomes 0. So, for this, there will be 0. So, for this, 0. Similarly, this CD basically situated outside the coil. So, therefore, for this is also 0. That means it does not affect the magnetic field within this coil. And similarly, DA, for this DA path, same thing is happening. That is, direction of the magnetic field and the direction of DL is perpendicular to each other. So, this is also 0. So, net magnetic field basically becomes B into L. Right? Only the first one. And so, according to the Ampere's law, what we know, that B dot DL equals to nothing but your mu I, right? So, therefore, B dot DL, the value of B dot DL becomes BL. So, BL equals to mu 0 I. So, B becomes mu 0 I by L. Now, if there is n number of winding, so it becomes capital N, mu 0 Ni by L. Now, this N by L factor, what you can say this? You can say this is the number of turn per unit length. N by L, number of turns per unit length. So, it becomes mu 0 Ni. So, the value of B becomes mu 0 Ni. So, therefore, within a solenoid, the amount of magnetic field can be determined by this factor mu 0 Ni. Okay. Hopefully, it is clear to all. Now, coming to the another parameters, that is basically the toroid. So, what do you mean by the toroid? So, similar kind of thing like the solenoid, but the difference is that for the toroid part, it is basically a circular plate. Okay. So, let us see what will be the what I can say figure of this toroid and what amount of magnetic field that is produces due to this due to the current passing through the coil at the center of this toroid. Okay. So, toroid, what will be the toroid? If this is a circular ring, then a toroid will be like this. A toroid will be like this. A circular path wind up with the coil. So, for this basically, if I consider a particular small dl here, if this is the direction of the B and or this is the direction of B and this is basically my dl, so basically similar kind of thing that is closed in according to the Ampere circuital law. Closed integral of B dot dl will be B into 2 pi r basically, right? So, this because B equals to mu 0 Ni. Ni means nothing but the number of turns. So, at the end of the day, the value of this B becomes mu 0 Ni by 2 pi r. So, similarly, N by 2 pi r is nothing but the number of turns per unit length for this circular path. So, therefore, it becomes mu 0 small n I. So you can see that for the toroid or solenoid, the value of the magnetic field remains same for each cases. Okay. So in this way, by applying the Ampere's law, we can easily find out the magnetic fields. Okay. Hopefully it's clear to you. In the next video, I am going to discuss about the force of a moving charge within a magnetic field and the Lorentz force. Thank you.